Have you ever tried to catch a curveball and miss? Or miss a hit in tennis because there was some weird spin to it? Why does that happen? The answer is the Magnus effect. When a ball spins, it drags a layer of air around it, and that layer of air spins with the ball. Say the ball travels to the right and spins clockwise. In sports like tennis, it is called topspin. The ball is moving to the right relative to the surrounding air, which is equivalent to saying that the surrounding air is moving to the left relative to the ball. So we will consider the ball's position as stationary and analyze the movements of air relative to the ball. As we have said before, there is a thin layer of air trapped around the ball, which follows a circular path, and the surrounding air is moving to the left relative to the ball. At the top of the ball, the thin layer of air trapped with the ball is moving to the right. The surrounding air and the thin layer of air at the top of the ball will clash together because they are moving in opposite directions, and the two streams of air come to a halt, so the speed is very close to zero. At the bottom of the ball, the thin layer of air trapped by the ball and the surrounding air are both moving to the left, so they add together and the speed of the air in this region would increase. The thin layer of air around the ball was going to go around in a circle, so up and round the ball. And the surrounding air, had there not been a ball, was going to go straight to the left. However, as I have just shown you, the surrounding air at the bottom of the ball just got dragged and combined with the thin layer of air, and this bigger and faster stream of air will go upwards. We say that the ball has exerted a force on the surrounding air. And when we talk about forces, Newtonian mechanics! And specifically, the three laws of motion, which will tell us how the ball and the air behave with forces on them. In 1687, the 44-year-old Isaac Newton published his book, Principia, which contains three laws of motion. The first law states that if an object does not experience a force, it will continue to go in a straight line at the same speed. The second law is an equation, where the force experienced by an object is used to accelerate or to speed up the object's mass. This is written as force equals mass times acceleration. The first and second laws really emphasize the importance of forces, pushes and pulls, which change the motion of objects. The third law is the key to unlocking the mystery of our spinning ball. It states that for every action force I do on the object, an equal but opposing reaction force will be exerted on me by the object. In simple terms, if I push on this car with a force F, the car will push on me back with an equal and opposing force minus F. The minus sign is there to indicate that the direction is opposite. Note that the first force F is exerted on the car and the second force minus F is exerted on me. The forces are not exerted on the same thing. But why is it that this car goes forward and I am not moving if we all experience the same force? According to Newton's second law, F equals ma. When the force is fixed, the higher the mass of the object, the less the acceleration. The lower the mass of the object, the higher the acceleration. Heavier objects are harder to accelerate. The car and I both experience the same force F, but because my mass is so much higher compared to the car, I am accelerated by almost nothing, while the car is accelerated by a lot. The point is, both objects, the car and I, experience the same force F in opposite directions. Now back to our ball in air. To recap, the ball drags the surrounding air upwards, basically exerting an upward force, F, on the surrounding air. Then the air must exert the same force minus F on the ball in the opposite direction, so the ball accelerates downwards and it changes its path to go down as well as continuing forwards. This is called the Magnus effect. The ball in this example is in topspin, and we can see the Magnus effect on the topspin very clearly in action with this inflated ball. What happens when the ball has a backspin, where the ball goes to the right, but it spins anti-clockwise? How do the forces work out? Pause the video, grab a piece of paper and a pencil, and go through the same process as we have done with the case with topspin. You should find that the ball is accelerated upwards, and it indeed does as I spin this inflated ball backwards. One example of the Magnus effect in real life is the banana kick in football, when a player kicks the football on its side. So the football has a sideways spin, like this. You can use this to get around the goalkeeper and score a goal. If that player kicks the ball on the right side, so the ball spins anti-clockwise as seen from above, the surrounding air at the top will be dragged down by the thin layer of air around the ball. So the ball curves up, following Newton's third law of action-reaction force pairs. How do different factors affect the size of the Magnus effect? What can we change about this ball to make it curve more? Well, we can make the mass lighter, right? Well, the force F that the air experiences is the same magnitude as the force minus F the ball experiences. From the second law of motion, we know that F equals ma. The lighter the ball, the smaller the mass, the more the ball is able to accelerate. So, the size of the Magnus effect is larger on a smaller ball. There are so many other factors that can affect the size of the Magnus effect or change the curvature of a ball, such as having seams on the ball, for example in baseball or football. The Magnus effect is truly complicated but fascinating. So this is the Magnus effect, the bending of a ball's path due to its spin. Hey, it's Q here. Thank you so much for watching this video. The next video I will be making is on the Bernoulli principle, which is also to do with airflow. So please hit subscribe and ring that bell to catch it. If you found this video cool, please hit like and subscribe and leave a comment down below to tell me what you think about this video. Thank you and have a good day.